Hello everyone, this is Dr. Fan. When learning gravitation, some people say the weight of astronaut in space station is weightless. Others might say the weight of the astronaut in space station is 90% of their weight on Earth. So who is correct? Actually, both answers can be correct. Why this is the case? Let's discuss it today. So why we can say the weight of astronaut in space station is 90% of their weight on the surface of Earth. On surface of Earth, we know the weight of any object Fg equals to mass times the small g, the gravitational acceleration, and the small g equals to 9.8 meter per second squared. But where does this weight come from? That actually comes from the law of universal gravitation. So the law of universal gravitation says between any object there is an attractive force, and that force equals to a constant times the mass of the first object and the mass of the second object, and then divided by their distance squared. And this attraction force is universal. So on the surface of Earth, any object has a weight because Earth is pulling all the objects. And this attractive force, in other words, the gravity, can also be expressed as g times the mass of Earth times the object's mass divided by the distance of the object to the center of Earth. In this case, it's basically the radius of Earth. So divided by RE squared. So this is the weight of any object on the surface of Earth. Then how about the weight of astronaut in space station? So although the astronaut is far away from Earth, but the law of universal gravitation is still valid. And we can find out the weight of astronaut in space station using this equation again. So let's say the weight of astronaut in space station is Fg prime, which equals to their mass times G prime. And it can also be expressed as big G times the mass of Earth times the mass of the astronaut divided by the distance squared. So now the distance has become larger because the distance of the astronaut to the center of Earth equals to the radius of Earth plus the height of the space station. Let's call it h. So here in this equation, I should have the radius of Earth plus the height of the space station and then squared. And if you compare this equation 1 and equation 2, their numerator is basically the same, and the only thing changed is their distance to the center of Earth. Because the astronaut's distance to the center of Earth is larger, so we know this Fg prime should be smaller. If we plug into the value, we should be able to find their ratio. So we know the radius of Earth is around 6,371 kilometers, and we know the height of space station is roughly about 400 kilometers. So if I substitute these two values, I should be able to find out the weight of the astronaut in space station. So for today's discussion, I'm interested in the weight of astronaut in space station compared to their weight on the surface of Earth. So I can use equation 2 divided by equation 1. Then I will get Fg prime divided by Fg equals to Re squared divided by Re plus h and square. And if you substitute all these values, you will get roughly 89%. So we can say that the weight of astronaut in space station is about 90% of their weight on the surface of Earth. So that's why this statement is correct. But why the other statement is also correct? Why we can also say that the astronaut in space station is weightless? This is because when we say weightless, we actually mean the apparent weight. So what is the apparent weight? Apparent weight is the normal force from the supporting surface or the skew. So what does this mean? This means we feel our weight because there is a surface or the skew resisting us or supporting us. If there's no supporting or resisting, we don't feel our weight. Just imagine you sit on a chair, you can feel your weight because the chair is pushing you. Or if you stand on the scale can support you. But imagine an astronaut stand on the scale in the space station. The weight will be 0. Why? If we do a free body diagram on the astronaut. So the astronaut is under gravity, Fg, but also there should be a normal force from the scale. And if we write down the net external force, we get normal force minus gravity equals to mass times acceleration. But we know for astronaut in space station, their acceleration is g. So in other words, this equals to minus mg. So we know Fg equals to mg. So this equation becomes Fn minus mg equals to minus mg. What does it mean? That means the normal force from the scale is 0. So there is no supporting force from the scale in the space station. And why is this the case? Because the scale and the astronaut and any other instrument in the space station, they are all under free falling. So since everybody is experiencing the same acceleration, there is no supporting force from the scale. So we can see all the astronauts in the space station, they are weightless. Just imagine you are playing skateboarding. When you jump into the air, the person and the skateboard, maybe they are in contact, but both are under gravitational acceleration. So there is no supporting force from the skateboard to the person. That's why the person will feel weightless. Okay? So this is why we can also say the weight of the astronaut in space station is 0. Or we can say the astronaut is weightless. So now you should be able to explain the weight of astronaut in space station. So if you are talking about apparent weight, which is the supporting force from the surface, the astronaut should be weightless because the astronaut, the instrument, and the space station are all free falling. So the astronaut cannot feel their weight. But if we are talking about the real weight of astronaut in space station, that is about 90% of their weight on the surface of Earth. And we can find that from the law of universal gravitation. Thank you for your attention. I will see you next time.